Hello, stats class. Here is lesson 8.2b, which is talking about working backwards with confidence intervals. But before we get to the working backwards, I want to remind you of a couple other things. So let's just kind of recap where we're at. We know we're going to take a sample and find p hat. And so say we know p hat and we know the confidence level C, which is usually 95%, but not always. Remember that p hat is our x value divided by our n value, or number of successes divided by the sample size. And believe it or not, these two or three pieces of information are all we really need to make a confidence interval, because what we've been doing is taking this information and using our p hat plus or minus our z star that we calculate from the confidence level times our standard error, which is p hat q hat over n. And so if we know what n is, we know what p hat is, so we can find q hat. We can plug in all those numbers into here and get this confidence interval, which has our two values, the lower bound and the upper bound of our interval. And we've been doing that forwards. We're going to talk today about working backwards a little bit. You saw a little bit of that in the warm-up, but before we work backwards, I want to point out to you that I kind of didn't tell you this last week, which you might get mad at me, but there's a calculator shortcut for this. If you have a graphing calculator, you might want to know about the shortcut. So I'll tell you the shortcut first, and then we'll talk about what if you're working backwards. So there is a menu for statistical inference on your calculator, and it is one of those things that we are going to do a lot of stuff on this list. If you go to stat, which is towards the top middle right here, stat, and then go sideways. We've done edit before, we've done calc and one variable stats before, and linreg. We have not explored this third menu that's the tests menu. And pretty much this whole semester, we're going to learn, believe it or not, almost everything on the tests menu sometime this semester. So there are a lot of things here we have not learned yet. There's a z-test and a t-test and a two-sample and a one proportion. Oh gosh, there's just a lot of stuff. We haven't learned any tests yet, but we have learned some intervals. There's a z-interval and a t-interval, and we haven't learned all of those yet either. It's just a long list. And what's funny is we're going to learn like everything on this list at some point this semester. It's crazy. I think there's one that we're not going to do this year. But the one that we know how to do right now is letter A. It's called, I'm going to put it so it's higher up on my screen. It's called the one proportion Z interval. So the only one we have learned so far is option A. And it might actually, now that I think about it, it might not be option A on every calculator, but I think it is on the 84s and 83s at least. The one proportion Z interval. This is an interval for a confidence interval for a single proportion. That kind of gives you a clue that later we'll be doing more than one proportion at a time. But if you choose that option, let's just have a look at what they want you to enter in this lovely calculator. They want three numbers, and they are X, N, and the confidence level. And you might recognize these numbers from the warm-up because that's where they came from. But let's just talk about what is X, what is N. X is that top number of p hat. It's the number of successes in your sample. N is the sample size. N will always represent the sample size, lowercase n, in this class. We will never use it for anything else. C level is confidence level, and that is was 0.9 in the warm-up, and so that's what I put there, but C is the confidence level. Because it has to know that in order to calculate Z star. But the calculator, believe it or not, only needs those three pieces of information. So you might recognize these numbers from something you had to calculate in the warm-up. It was the number of red beans out of a sample of 254 beans. That's a lot of beans. Maybe I used a really big cup that time or something. So my example is X is 108 red beans. N is 254 beans in the sample. That's our sample size, and then we were trying to be 90% confident. And we did this backwards in the warm-up, but I'm doing it the same numbers now just to say this is where I got that interval from in the warm-up. So if I type all that in, which I already did, and then I choose calculate, it does, actually I'll just not show you that quite yet now that I think about it. What the calculator does is it does the 108 out of the 254, and it adds and subtracts the Z star for 90%, which is 1.645. You had to calculate that a bit ago in the warm-up. And then it does this 108 out of 254 times 1 minus that, and divided by the 254. So the calculator does all of this in one amazingly fast step. And I'm actually going to go back on my calculator so you can see how fast it really is. It's amazing. So I just typed all this stuff, and when I hit calculate, it just goes poof, there's your confidence interval. Isn't that amazing? So it gives you the confidence interval of 0.374, and I'm not going to put all those digits, 0.476. This is the interval I gave you in the warm-up, and I made you work backwards to find the number of red beans and all of that. So I wanted to show you that is a super fast way to get your interval. However, please be cautious about this, because on the AP test, if you don't write any of this stuff and you just write that, they will mark you down for not showing work. So my advice is write this out and prove that you know the formula, and then use the calculator shortcut. So don't skip this step of writing everything out. I will also mark you down if you don't show enough work. So if you just use the shortcut and write the answer, that is not enough. And that's why I didn't tell you this last week in lesson 8.2a, so that you would not make that mistake. So anyway, that's a really short, fast way of making your calculator do the magic. These three numbers are what it needs, and it gets you an answer. One more thing I want to say about that, and that is if you happen to notice he had his 0.425 and a whole bunch of decimals, it got that by doing the 108 over 254. And if you round this off, you're going to get inaccurate values. So like if you take 0.425 times the sample size, which is 254, you get this 107.95, which is impossible for the amount of beans, right? You can't have 0.95 of a bean. We're just going to count it as a whole bean, and it's 108. If you go into this calculator shortcut, which is really amazing, but if you accidentally did 0.425 times 254, and you got this decimal, it will give you an error. It can't handle this being a decimal. So look at that. It knows that it's supposed to be a whole number. So then you just have to go back in and make it into a whole number. In fact, you could type the whole thing here like I just did. You could type 0.425 times 254, and then notice it's a decimal and change it, which is what you should do. So change it to the nearest whole number, and then the calculator can handle it. So that is the calculator shortcut, and I wanted to start with that. So I hope that you will remember, well, maybe I should write it down. These numbers have to be whole numbers, or else the calculator just can't deal with it. All right, next I want to talk about working backwards, which is the title of this lesson. We actually worked backwards a little bit in the warm-up, and that was to introduce you to the idea that you could work backwards. But a very common thing that statisticians have to do is they often know in advance what margin of error they want, and they have to figure out what sample size will accomplish that. So here's something practical that you would do if you were about to gather data and you're trying to figure out just how big does that sample need to be to get me a narrow enough interval for what I'm supposed to do. So let's talk about that. For example, I'm just going to go straight to an example. Let's go to 95% this time. We want to do a 95% confidence interval for some proportion that we have not estimated yet. And we want our prediction to be pretty close to the true thing. And a lot of times there's some legal reason why we need to be within a certain value, or, you know, we know how close we want to be. Let's say we want to be within 4% of the actual value. Okay, so I'm picturing my little confidence interval thing. I want this to be 4%. Within means or less. 4% or less. Margin of error, which is half the length of my interval. So that's my goal. And the question is, how do I accomplish that? Okay, so that within 4% means my margin of error has to be less than or equal to 0.04. I want to have a p hat plus or minus 0.04 or less. That's my goal. And knowing that goal, we can work with that because we know what the margin of error formula is. So the formula for margin of error is z star times the square root of p hat q hat over n. And that has to be less than or equal to 0.04. So then the question is, do we know any of these numbers yet? I didn't give you a whole lot. Did you notice I didn't give you a sample because we haven't taken our sample yet? I didn't give you a population proportion because we really don't know what that is. But what you can do is you can say, okay, I can find Z star at least 95%. So I'm going to calculate Z star based on 95%. That's inverse norm. Remember, it's the 95% plus a little bit more, so 95% plus half of the extra 5%, and somebody in class would probably tell me what that is. It is 975. So inverse norm of 0.975 gives you the Z star. It's 1.96. I happen to have that one memorized because it's so common. So Z star is great. I know that. Yay. What about p hat? Do I know p hat? Oh, gee, I don't know p hat. I don't know q hat. I don't know n. That's a problem. I know I'm going to find n in a minute here. If you have no idea what p hat is, there's a rule of thumb for that. If you do know what p hat is, you use it, obviously. So like with this beans thing, I would use the 0.4, whatever it was, 425. With a situation like this where we have no idea, if you have no clue, you're going to use something right smack in the middle, which is 0.5, because I know that p hat is somewhere between 0 and 1, and if I have no idea where it is, I'm going to choose the one in the middle. Okay, so I'm just telling you that's the general rule. You use 0.5 only if you don't know what p hat is. Okay, so I'll use 0.5. 0.5. And then if it turns out to be something different, that's not a big deal. And then after that, it's algebra. Some of you are going to be really happy about that because you're good at algebra, and others of you that your stress level just went up a little because, oh my goodness, you have to remember algebra. That's okay. Either way, we're going to talk about it. This square root thingy goes over all three numbers. The n is part of the square root, so I could rewrite this as square root of 0.5 times 0.5 over square root of n. That would look a little bit better because what I need to do is get this n moved over to the other side. So I'm going to talk through the algebra in case you need that. If you are really good at algebra, I suggest you pause the video and go try it on your own. You probably could do it, but just in case, I'll talk you through it. So that square root of n gets multiplied on both sides, and that cancels this one. And then I have to get the 0.04 off of this side, which means I'm going to divide both sides by 0.04. So I've got 1.96 square root of p hat q hat, except I don't know what they are, so I'm estimating them, and over 0.04 less than or equal to square root of n. And then I have to get the square root off of there, so I'm going to square both sides. So it's a little bit messy, but that's okay. I can handle it. The square actually gets rid of this square root, and so then I have 1.96 squared. I have 0.5 times 0.5, and I'm purposely not multiplying them together because usually they would not be the same number. Well, sometimes they will. If you have no clue, they're the same number, and otherwise they wouldn't be. And then the bottom also gets squared, 0.04 squared. This whole thing gets squared to estimate n. So all of that messing around was the algebra part. I'm going to type that in my calculator. I need to get out of there first, and I'm going to say 1.96 squared times 0.5. I could just do 0.5 squared, but I'm trying to emphasize that it might not always be the same number twice. 0.04 squared. N has to be 600.25 is less than or equal to n. All right. So will a sample of size 600 be big enough? I'm hoping if we were in class, somebody would say no. And the reason is this little symbol right here is not an equals. It's a less than or equal to, or n has to be bigger than or equal to this. I'm going to round it up always round up on this type of problem to n equals 601. That is my minimum sample size that I would need to get that particular margin of error. All right, so that's just working backwards with algebra. And you could, if you wanted to, do the algebra every time like I just did. There's one other way to do it. So one method is plug in whatever you know and then solve for n. The other method is solve for n before you plug in everything. And so this last piece is optional because you could just do that, what I just did. Pardon me while I get my computer to behave. I'm hoping that my video is still going. Yeah, well, there's going to be this awkward pause. That's okay. My computer fell asleep. All right, so hopefully I'm still going. Looks like my video is still going, so that's good. Optional, you could just learn or derive and then learn a new formula, and that's also an option for you. So if you like the method I just did, you don't have to write down this piece, but I'll say that you could start off with z star times square root of p hat q hat over n less than or equal to margin of error, and then you could solve this. So basically, you would multiply by square root of n and you divide by margin of error, and I'm going to just do that all in one step because I did it the long way before. So the margin of error ends up down here, and the square root of n ends up over there. Multiply by that, divide by that. Got it. And then you square both sides. And you end up with, I'm going to write it this way, with n is greater than or equal to this whole thing squared. I'm going to simplify it a little bit by saying z star squared times p hat q hat without the square root because that canceled. And on the bottom, I have the margin of error squared. So you could memorize this formula or put it on your weekly summary so that you have it. But this is the formula you would use if you are finding a sample size for a confidence interval for a proportion. And of course, when we switch to other things besides proportions, we'll have to get a different formula for that. But anytime you have proportions and you want to know your sample size to get a certain margin of error, this is how you do it. And that's your choice. You could either always plug in the numbers and then solve, or you could use this formula and just plug in the numbers. A few less steps that way, maybe. All right, that is enough notes for now, and I will come back to you in lesson 8.2c, which is coming up next.